trends of exciting research areas such as 3D and then multimedia and then also VR, AR topics. We are very happy to bring all the experts in the food domain here, and then also want to invite all the general CVPR community to look into our food domain challenges and to explore and deal with some of the challenges we have in the food domain. It is a very exciting period now, so thank you all for coming and joining us, and then we want to grow this community as we go. So thanks all for coming, and those are all the organizing committee members, and then we thank everyone who helped us to make this happen. Thank you, and slide. Yeah, so in terms of topics, we actually have a quite wide variety of topics. We have like 13 papers in our workshop, and then which will cover topics from fine-grained food recognition, multimodal food models, and portion estimation, continuous learning, food instant segmentation, food image generation, volume estimation, via 3D object reconstruction. And this is the stack schedule for today. At 8:40, we have an invited talk from Dr. Pratia Radva. And 9:40, we'll have our first oral session, then we will take a coffee break at 10, which will be upstairs, I believe, on the 4th floor. And then when you come back at 11, then we will have our second invited talk from Dr. Chong Wang, and then followed by an oral presentation. Finally, we will announce our challenge winners, and then they will give us short presentations about their method. So those are the oral presentations, and then I will show the poster later. So next, so we will have we can start with our first invited talk, and Professor Zhu will introduce our first speaker. Yeah, we are ready. Thank you.
I think I can go without the mic. So I'm very happy to introduce Dr. Pratia Radva, who is a full professor at the University of Barcelona, head of the Consolidated Research Group, Artificial Intelligence and Biomedical Applications. So she has published in more than 20 journals and international peer review conferences on food image analysis, and led the IP5 European and national projects that are related to the application of deep learning for non-intrusive food intake monitoring. So let's welcome Dr. Radva for this. You should be able to. Yes.
Maybe it's also short.
Okay, thank you. So thank you very much for inviting me. This is a very special invitation for me because data food computing has been my main topic last 10 years. Today I want to explain what is going on in our group. We are teams of 12 persons, so I will not have time to go into detail, but I would like at least to show what kind of questions we are doing. So why are we staying here in a MetaFood workshop? Because as this graphic shows, food recognition and food data analysis is becoming more and more popular. So here you can see the number of papers that are appearing in the Web of Science. So in 1990, there were 3, 4, 5. Then in 2010, there were like 30, 50. But you see that just from 2017, we have per year around 100, 200, even 300 papers. So this topic is really getting very, very popular and very important. And when we speak about food computing, we speak about food recognition, we speak about food detection, retrieval, and segmentation, and so many problems. One of the very important issues to get more and more popular is because we have very nice also data sets and we have very nice challenges. And the first challenge was in 2011 in the iFood that was presented in the CVPR. But then we have today AI crowd, we had large fine food AI with 1,000 fine-grained food categories. And I especially would like to congratulate for the very interesting and challenging challenge on 3D reconstruction that is in the MetaFood CVPR version. Now, why is food recognition a challenge? Because if we look at such kind of very small subset of food data, we can see how complicated and how difficult is the problem. If I ask you here, for example, what is in this image? What is in this image? What kind of food do you see in this image?
Yeah, that's good. What is it? Salami?
Salami, it could be salami, it could be tomato, right? It could be carpaccio, it could be very different things, right? If we look, for example, for here, for example, it is even much more difficult. So we see that food recognition and food data analysis is really challenging. And I would like to ask the audience, what kind of problem that first of all, is there anybody that has never seen the food image analysis problem? That is, all of you are working on food image analysis, I guess. Anybody is just opening new? No. And what are the problems of food image analysis you found? Why is the problem difficult to you?
I'm surprised that it's the diversity.
Right? We have high interclass variability and high interclass similarity, right? If we think about carpaccio and tomato and salami, they look very similar and they're different categories. But if we think about all appearance of tiramisu, it could appear like cake, like plum, like in very, very different way. But what else? What else? What other problems do you see there are?
Forms like ads. Boil that, we'll try that.
Right? We have very fine-grained problem, right? That is, we have some classes that are really, really very, very similar. We have ambiguity. It is very difficult to decide one category and to separate from another category. We have a lot of uncertainty in the data because even when we create our data, our images can be very noisy, can be very ambiguous. Our annotation can be ambiguous. We have scalability problem. How many food categories do you think there are all over the world? 1,000, right?
Well, I think it depends on how you define categories.
Right, but then we go back to the ambiguity problem, right? So when we go for the scalability and we want to put more and more classes, I trained my algorithms in Europe, but then I come to the United States. I want to add new classes, but then how to assure that my models are not forgetting previous classes. So we have the problem of data forgetting. We have long tail distribution, right? Because if we see all these categories, for some of the categories, probably for pizza, we will have thousands and thousands and thousands, but if we go for very specific dishes, we will not have so many images. We have lack of annotated data, right? Because if we have thousands and thousands of categories, how to ensure that we have thousands or millions of annotated data? This is really very slow, very tedious. And we have a lot of knowledge about food. If we go and look at all recipes, all documents that are written about food, we can see that there are a lot of relations between different concepts, right? We have recipes, we have ingredients, we have relations, we have instructions in very different formats. We have videos, we have images, text, we can have ontologies, etc. So how to put this knowledge representation into the deep learning model that usually is done on images? So you see here we have a lot of different problems, and this in fact reminds me very, very much many years ago in 1995 when the computer vision community began to work on face recognition. And you are very young, so at this time you were maybe in school or before, but I remember that at this time when we were speaking about face recognition, and everybody was thinking, oh, this will never be a reality. It's like scientific problem, okay, so let's work on the yellow face data set and or AR data set where we have like 20 faces, 20 identities, and then the big advance was to recognize 20 persons, right? So you can imagine that if today we are speaking about like face recognition, like solved problem, right? So you can imagine, okay, how long way it was from 1995 until here. So face analysis at this time boosted computer vision research. And my feeling here is that food data analysis also has the potential to boost forward the computer vision and deep learning research. Because if you have difficult problem, then you can solve and you can develop complicated and powerful problems. If we have a very simple problem, so you don't need very complex models. So here, just to illustrate, as we mentioned already, the interclass variability. Here, for example, you see all these apple pies that are looking very different, but they are the same. And at the same time, you have the tomato sauce and curry sauce that look very similar, but they are different. We have this fine-grained recognition problem where we have different classes that are appearing very, very similar. We speak about scalability. Scalability means to be able to recognize thousands of classes. But if you go to the data set in general and for computer vision, you see that most of the data sets that are used today, like they are still having like much less than 1 million of images, and they have much less than 1,000 of classes. So most of like event, we always go back to CIFAR 10, CIFAR 100, where we have only 10 or 100 classes, but this for sure is not enough if we want to solve the problem of food recognition. And that's why this is a very nice work, the large scale visual food recognition and data set that was published last year. And here you can find this data set that has more than 1 million of images, and they increase it up to 2,000 classes. So this is a very nice data set in order to test our algorithms and to develop and improve our algorithms. And the nice part is that also you have a very nice relation between the dishes, categories, recipes, etc. So, but if we think about what we really need, okay, so let us think and make some kind of parallelism. Today, still most of the handy data sets is the food 101, We go back 10 years ago, and this Food 101 has 101 classes. It has 101,000 of images, but we have also some others like Foodix, like Foodwek, etc. If we compare to the ImageNet, that is like our baseline data set, we have 1,000 of categories and 1,400,000 of images. But how many classes we should recognize? If we think about Wikipedia, Wikipedia says that there are 200,000 basic classes. Do you know any classifier that is able to recognize 200,000 classes? Me not. And the question is that if we have 200,000 of classes, how many images do we need in order to recognize 200,000 classes? So here the scalability is really still an open problem, okay? But, and of course, as logic, the higher the number of classes, the performance drops automatically. So it's not only important to have classifiers working, but they should work well on this scalable problem. However, today we have a lot of images in there. Okay, so we scrap, we can find millions and millions of images. And even they are non-annotated, we still can take some profit of them. So we can leverage from this huge amount of non-annotated data. And this is called self-supervised learning. Okay, and this is one of the things I would like to comment you. So to summarize, today we have some very powerful technology. We speak about deep learning. Deep learning is able to make autonomous car on the street. So for sure, it should be also helpful to help to food data analysis, right? So we want these algorithms to be able from an image to say, okay, this is here cut noodles and pasta, this is spaghetti carbonara, the ingredients are this, and you can cook in this way. But how? It's not so logic, so magic. It's not just putting data and train, because the problems are really complicated, as we mentioned. So today, that's why we need data-centric food analysis. And here there are some of the challenges today of deep learning that deserve attention in order to push forward the deep learning models. And this is generic, not only for food, but as I mentioned, all these problems for food data analysis are very, very relevant. So because we don't have so huge amount of annotated data, we should do transfer learning. We can do transfer learning. We can translate from one domain to another domain. We can solve different tasks like recognizing at the same moment dishes, ingredients, and recipes. And in this case, we can help each other, each task to the other. We also should work on uncertainty modeling in order to manage all this uncertainty that is in the data and in the models. And this is, I will try to illustrate some methods for this. We should work on self-supervised learning, how to take benefit of all this huge amount of data. We should look on efficient and model compression approaches, because we want to solve this problem of scalability. So are we able to really come up with classifiers of 100,000 of classes? And even if we want to have maybe 1,000 of classes, still it's not so easy even on ImageNet to work on a computer with 1 or 2 GPUs. So how to come up with these efficient models that do not need millions and millions of images. This is part of the efficient learning approach. And then also we should think about how to advance in the meta learning techniques that are exploring how models are able to learn. And inspired on this, we are working also in continuous learning, how models that are trained in one set of classes can be increased incrementally without forgetting the new one. Then also generative AI, of course, everywhere generative AI at this moment is helping in solving such problems like in creating synthetic data. But how can we use it in our case? And I will give you an example, how to do multimodal learning, taking into account that data today are in different modalities like text, images, videos. So how to take benefit of this knowledge representation graphs into the deep learning models, how to create explainable AI, and how to apply to real problems. So all these are some of the aspects that we are working on, and I will try very briefly give you an idea about our work. But you see that still in food image analysis, we are at the beginning. Still, there is a lot of space for work to solve interesting questions and to create interesting problems. And these are all on different lines of research we are working with this. And I would like to begin with self-supervising for photo recognition. So self-supervised learning is helping, everything okay? Yeah. Self-supervised learning is helping in one of the very important pitfalls of deep learning models, that neural networks are dragons, but they are greedy dragons. They need a lot of data. So how to help to this, what we do, what all of us we do when we begin learning data, the deep learning models, is to do data augmentation, right? So you get image, you do all kind of distortions and deformations, change contrast, etc. So if you do 10 simple transformations, you automatically augment 10 times your data. Okay, and then you train your models, but sometimes this data augmentation is too simple in order to be really helpful. So we need more data, and what we decide to do is we go to internet, we get a lot of data, a lot of other images, we don't know what they are, and then we want to use this data in order to make our models more robust. The point is that when we get this data, in fact, we don't have any information what these data are. If they are medical images, if they are from ImageNet, whatever, or they are related to food. So the question here is it possible to leverage from such kind of data if we don't have any information about them? And for this, self-supervised learning says yes. The idea here is, okay, if I have different classes, like different letters in different languages, in different alphabets, okay, what you see here is that I don't know which languages these are, but I still see that these are two similar, and these three are much more similar, and these two are similar and different between. So in some way, I can use this similarity, and then whatever word I have, and that I want that this similarity, that is my model, is keeping this similarity as small as possible, and this difference from different groups as different as possible. And the nice part is that self-supervised learning can express this as a loss function, just putting this distance as small as possible and this distance as big as possible. And this is called the contrastive loss. Now, the idea in the self-supervised learning is that if I have a lot of data that have no labels, okay, and I have small amount of data for which I have labels, so the idea is to use this huge amount of data to pre-train my model to be robust enough so that if my model is really very good, when I train on smaller amount of data, I will have much faster and good and better performance. And this, I should say, is that attracting a lot of attention to the community. And here there is a very nice tutorial. I would recommend you to look at this of LeCun. And here on this graphic, you can see how the number of self-supervised learning is incrementing just last years. and big advances are occurring just 4 or 5 years at most. And what is really nice is that if you do such kind of robust models, just using non-annotated data, then you can use even as feature extraction, and you can approach the performance of supervised learning training models. Okay, so for example, here you can see that to supervise, this is the performance of supervised models, and this is the performance of self-supervised learning that is just trained by images that are not labeled. Okay, and the interesting part is that self-supervised learning is kind of working similarly similar to the human brain. I mean that if you think about babies in the very first months of their life, they don't have any communication channel, right? If we say this is dog, this is cat, they don't understand. So they are learning a lot in unsupervised way. Okay, and then once they begin to learning in this unsupervised way, then at some moment they begin to also understand slowly the semantics of words. So they should combine these two lines of supervised and unsupervised learning. And this is also interesting that neuroscientists are working, showing this parallelism between the human intelligence, how human beings learn, and show that there is a lot of similarity with the self-supervised learning. Basically, the hypothesis here, you see this neuroscientist, computational neuroscience from McGill University in Milan, and he proved that there are two processes that are occurring in parallel. One is this is the ventrovisual pathway that is responsible for recognizing objects, and that is doing supervised learning, taking into account the semantics of the concepts. And there is the dorsal visual pathway where we are aware of something is happening, but we are doing without any semantics. That is, this is done in a very unsupervised way. And at the end, these two processes converge, and that's why we're understanding what happens in the reality. So you see that it's very nice that deep learning also is helping to understand how we work. And here you see that one of the very good and one of the, you see, well, early models, it is from 2020. This was the SimCLR method created by Google AI team, where they say, okay, I have an image, I do different data augmentation. I don't know it is a dog, okay? But I know that it is the same image, right? So when it passed through my neural network, I want that the final classification is the same, whatever it is. If it is wrong or right, but it should be the same. Now, it doesn't make sense to say different things because I'm having the same semantics. But if I have two different images, it's highly probable they are representing different concepts. So when I make this process, I want that the final embeddings of different images is as far as possible, and the final distance between the embeddings from the same image after different data augmentation is as close as possible. Okay, and this method is really working very nice. So now in this case we speak about positive, but when we compare different crops or different data augmentation from the same image, and negative when we have different images. So we want that the positive sampling is as small as possible, as close as possible, and negative sampling is as big as possible. But if we think about all kinds of possible negative sampling, of course, if I have millions of images, I can have much more pairs of images. So the problem is really exponentially complicated. So some of the researchers, they asked, is it possible just to focus on the positive sampling and not compare every image to every other image. In this case, we speak about positive sampling. And these methods, Biol and Simsiam, they are trying to do this, and they propose some interesting solutions. But for this case, it is possible that if we are only focused on positive sampling and we want the different crops of positive sampling is as close as possible, then easily we can come up with trivial solution. What happens if the answer, if the output of my model is 0? 0 minus 0 is always 0, right? So loss function will be 0 and my model will not learn anymore. So for this, to solve this problem, there is the Barlow twins that was presented in 2021. And here they say, okay, in order to avoid this trivial solution, right, what I want to do is I'm not comparing image to image, but I'm comparing feature to feature that is extracted from the image. That is, if I pass through the model and then I have my embedding, okay, and I can think that my embedding is returning like a vector of 10 features. So maybe first features corresponding to head, second features correspond to the background, third features corresponding to the color, fourth features corresponding to the food of the person, etc. So I want that the food in the one image, one crop, and the foods in the other crops are as similar as possible. So I want that this difference is as small as possible, but I want that the embedding on foot and head is as different as possible. I don't want that foot and head are the same thing. Okay, so that's why they consider this correlation matrix of features, and they say that I want in the diagonal to be 0, that is food in different crops should be the food, but other parts, that is different parts, should be as similar as possible. Still, self-supervised learning is learning so fast that you know what happens when we learn very fast. In this case, we overfit. Okay, so we really need to make the life of the self-supervised learning model difficult so that it is not overfitting so easily. So here there is the NNCLR method that is very elegant. It says, okay, I have my images, okay, I do different crops or different documentations, and then I pass through my encoder. So I have my embedding in this latent space. So instead of comparing first embedding versus the embedding of the other image, I look for the nearest neighbor in this latent space, and then I want that the nearest neighbor is as close as possible to the embedding from the other crop. So it means that I want in some way my representation in my latent space put similar semantical images in the same space. So if I have a turtle, I go to the latent space, I get the closer turtle, and I want that this different turtle, because this is different points in my latent space, is as close as possible to the turtle going through the different branch, being overpassed a different crop. Okay, so this improved the SimSiam and SimCLR, and then we decided to go further, and we said, okay, shall we just keep the first neighbors? Okay, maybe you can go for k neighbors, but if we go for k neighbors, what is the right k? 3, 5, 7, 11. Okay, we decided to go for x neighbors, but then in order to decide, in order to think about how to compare neighbors to neighbors, we decide to make the centroid of the different neighbors. Okay, so if I have the centroid of the different neighbors, that is obtained from one of the crops, and embedded by the model, and then I go for different crops, and then I project it in my latent space. I have the neighbors, and then I want that these centroids are as similar as possible. That is, I expect that all turtles stay very similar, very close in the latent space. And then if we want to go and make it even more difficult for the self-supervised learning model, we decided to change the distance. So instead of just comparing Euclidean distance between this embedding and this embedding, we decided to use transformers. Why transformers? Because transformers are having the ability to highlight the important parts of the images or the important features of my image, right? So if I have my model, my images that are obtained by one of the branch of my self-supervised learning model, and then I have the same images with different crops. So I pass through a transformer, and transformer is kind of focusing on the parts that are really important for my images, and they are disregarding other parts, other features that are not important. That is, the transform is really taking into account the semantics of my representation in the Latin space. Okay, and this is the way in order to obtain the centroid. So let us show you that our model. This is on one hand, this is one of the branch. So we get the image, we do the cropping, we pass through one of the models, the branches of our self-supervised learning. We go to the Latin space, we get the KNN, that is the K nearest neighbors. Then we pass them through the transformers, and we get this centroid representation. Then we go on the other branch, we do another crop, and then we go into the Latin space, we get the nearest neighbors, and then we pass them through the transformer, and then we get the centroids. And now we want that these two centroids are as closer as possible. Okay. Okay, so this was presented last year in the ICCV in Paris, and these are some results. We applied on different data sets. Of course, when you do self-supervised learning, we should go for to compare to others. So you need anyway to go to CIFAR 10, to CIFAR 100. So you see that we could beat in top 1 and top 5 all these state-of-the-art methods. And did the method, and also we did also we showed that we are beating the ImageNet 100. And here you can see how our data are represented. So here you see all images that are represented in the Latin space in epoch 1 at the beginning. So as expected, everything is very mixed. Okay, when our model is trained 100 epochs. So you see that different classes are getting are separated. In 400 and in 999, so you see the different classes are very well separated. And you see everything is done in an unsupervised way. So here we know the labels because we are using ImageNet, but our model, our self-supervised model, all for one, it doesn't know if they belong to the same class or not. And anyway, it is learning to separate very well the different classes. So this is behind this data-centric, why we speak about data-centric food computing, because we are very much focusing on the data. We are thinking basically, principally on the data and not so much on what is the model. But when we speak about data-centric food computing, we also can think about other aspects as I mentioned in the beginning. Like, for example, what is the uncertainty in our data and how to make our model taking into account the uncertainty of our data, because our data always will have some errors, and how to use this uncertainty to improve the model. That is even more interesting. So here I can show very fast other approaches that, for example, are considering the certainty. So as I mentioned, data augmentation is very important. When we do we get the images, we do different data augmentation in order to improve. We can use simple data augmentation, or we can even generate some synthetic images in order to help our classifier. Like here, for example, these images are synthetic images and they are looking very nice, I would say. Now, the question is, when you do data augmentation, So do we think about our data? Going back to the data-centric analysis. Usually, when we do data augmentation, we get data and then we apply some kind of data augmentation, right? Cropping, change, contrast change, or synthetic data. Let us imagine we have this example. I have these two classes and I train a classifier, okay? And here you can see that I have some outliers and some underrepresented part of my data, right? So if I get randomly some data and make another data augmentation, where will the new data be? If I get some data, that is, I get randomly from here data and I do data augmentation, so they will change in their Latin representation, but they will be quite close. So probably because I have most of the data, they are on the right. So the new generated data also will be where is the most distribution. So in this case, I'm not helping to my model because in fact, I'm even making stronger that this is the son of the dark brown class. So the question here is maybe I should focus on underrepresented data and do data augmentation in this uncertainty aware way. Okay, so what we do is, for example, here they get the synthetic, the SynGAN model, but we focus on the data that are wrongly classified, and we create the data augmented from such kind of data. And okay, just I would like to give a much brief overview of the different work we are doing. Next, the other question here is that when we have the problem of food image analysis, we need annotated data. So always data annotations are done by people, by human beings, right? And always when you have persons, you have errors because people are not perfect, right? So it means that in our case, for sure, we will have a lot of noisy annotated data. So here there is a very nice video, it's not mine, that show these are the errors that are in ImageNet. So when you train your models in ImageNet, you see how many errors you have in your model, in your data. Okay. So usually what has been shown in the bibliography is that if you get all the data sets, all public data sets, in average, you will find that your data have 3.4% of errors, okay? Even if you have CIFAR 10 and CIFAR 100, even if you have MNIST that is so simple, like toy problem, you still will have a lot of errors, okay? So if you read some paper that gets like 99% of accuracy, do you believe it? Good. So now the question here is, can we come up with some robust models that are able to learn even with noisy labels? This is the challenge. So there is a very nice model in the bibliography that is called divide mix. And this model, it was published 2 years ago. And in this case, the author showed that if you have if you get a data set and then you train two models, A and B, and then you apply a classification. So some of some of the training and validation data will be correctly classified. Some of them will be wrongly classified. So what divide mix says is, okay, if you get this wrongly classified and treat them as unlabeled because they probably will have labels in their annotations, and then make the other model focus on this unlabeled data. So in this case, you can guess what are the labels in the annotations and make more robust classification. So here you see that I train my model A and B with different random sampling, etc., but they are trained on the same data set. I look at the likelihood. You see that here the likelihood, this is the clean, that is, some of them are classified with very small loss, so I treat them as clean, and some of the data are classified wrongly. They have very high loss, so I treat them as noisy. So now each of the model, and the model A treats the errors of model B as unlabeled and vice versa. Okay, so what we did is we went one step further, and we showed that in fact this approach is much more robust when you treat each class separately. That's why it is class conditional model. So we do this separation between clean and hypothetically wrong labels, class per class, and in this case we improved the results. So here you see this is the class conditional noisy labeling model. So it improved the divide mix on different data sets, CIFAR 10, CIFAR 100. It improved. And this was presented in an Iberian conference, international conference on petrocognition, and it got the best paper. And then we decided to go one step further. And then we thought, okay, we know that our data they have a lot of uncertainty. So when I use my data in order to create data augmentation in the middle stages of my model, so I can be guided by the uncertainty of this data and focus on the zones when I have higher uncertainty, where I mean that my model needs to focus and to work hardly on this part of the latent space. So in the Bayesian divide mix, we published it in Neural Networks this year. What we do is, okay, we have the data, we create both models, A and B, okay? With this A and B, we look at which are the well-classified data we treat as clean, wrongly classified data we can treat as noisy. We treat that is the noisy labels for each of the model is treated by the other, okay? So here what we do is we try to learn only from the clean and classify the noisy. And then we do the data augmentation from these images, from the clean and noisy, but taking into account where we have the highest uncertainty of my data. Because when we have the highest uncertainty, means that these are the data where my model still doesn't know how to classify and where it should work and focus and go deeper. Okay, and that's why we call it Bayesian divide mix model. So here you can see the results on CIFAR 100, for example. So we have the Bayesian divide mix nicely improved all different other models from the bibliography. And you see that we did this test with different amount of noise. We put 20% of noise in our data, 50% of noise of our data, 80% of noise, and 90% of noise. And you say, wow, if you have 90% of noise, how is it that it is working? Well, if I have 100 classes, okay, and I get in my training data set, I put 90% of error, this error will be distributed all over the classes. If they are distributed on one class, then my model will have a problem. But because it is distributed on different classes, so still my model is able to treat the data properly. Okay. Good, fine-grained recognition and prompt learning. As I mentioned, data analysis is very fine-grained. We have different classes that are very close. So how to treat them? If we have the same model, and we want that our model is able to treat at least 1,000 of classes, where some of the classes are much closer or much more mixed than others, it will be very difficult. So we should apply the divide and conquer approach strategy, you know. So what we do is, okay, let's focus on these zones, on this subset of classes that are really very similar. Let us focus on all the classes that are pasta, all the classes that are beans, all the classes that are, I don't see here what is this. So, and then we have different models that are specialized on these groups of the classes. Now, one is focused on spaghetti, one is on pasta, one is focused on pizza, etc. So now, and then I will combine these different classifiers with the generic classifier. Okay, in this case, I will have much better performance. So here you can see that what we do is, in fact, our model is we create this subset of classes. We have one of a classifier for each of these subset of classes, and then like multitask framework, we put together and we train and then the one big model that is combining the votes of the different classifiers. And here you can see that in fact the classification is quite good. And here, this is the ground truth, ACROL. This will be the original baseline, we'll say bacon and eggs. That is still close, but this combined fine-grained recognition model, we will say that it is ACROL. Okay, it defines it correctly. And then, of course, today we have very nice large language models, of course. We will see, I'm sure we will see a lot of large language, we will hear a lot of approaches about large language models. Well, let's go for this and use it. And then here, in this case, what we do is we can use this textual prompt that could be generated. This is the nice part in food domain, that we can create very different prompts that are coming from ingredients, from class representation, from category representation, from recipes, from very different ways. Okay, we can create these prompts and then we can embed them and use them in order to improve our model. So I will not go into detail because we will present it a special continuation of this work. This work was presented last year in Madima, but we went deeper and we presented our results on this approach. So here you see very nice. This is very nice clustering in the latent space of the different classes and how this prompt learning is helping to improve the problem of fine-grained recognition. And then food ontology, as I mentioned at the beginning, we have a lot of knowledge about the different concepts in food. So how can we use them? So there are a lot of people that are from semantic ontology, from natural language processing, etc., that are working on ontology. But there are not so many people working on how to put ontologies into the deep learning models. So in this case, what we were doing, we constructed this semantic graph, this knowledge graph representation that is relating each of the food concepts to each of the ingredients and other food concepts. So we know that, for example, if it is a soap, probably it is not tiramisu, right? Or if it is strawberry, probably it's not appearing together with meat. So if we use this ontology, we can compute the probability of co-appearance, this correlation between different concepts, and then we can use this information in our models in order to help to take decisions, especially when the decision is hard to take. That is when the likelihood is not very high, confidence is not high. So here you see that, okay, we have our model, and we have this semantic matrix, this matrix that is representing the co-occurrence of different concepts, food concepts. And our model is taking into account this relationship in order to take decision what is in the image. So there is a very nice a mathematical representation, how to compare and to put into our model, into the loss function, this co-occurrence probability of the different food concepts. I won't go into detail. Okay, so and here you see the results that when we have for multi-label, if we have images, we want to recognize different ingredients. So this is a multi-label classification problem. And if we try to recognize just food category, this is single label. So you see that taking into account the ontology is allowing also to make the model much better. And last but not least, volume estimation. This is the problem, to me, the problem of the century. How to estimate the volume. And I think we will hear today about the food volume estimation. So I just brought you some videos. These videos are from Nutrition 5K. And here we use different generative AI models like NERS in particular. And this work was submitted to ECCB, so we are waiting for the results. Good. So just to finish, I like the domain that the food recognition is so hard. So that's why it puts us nice challenges to think about how to solve this problem, very complex problem, but also it has very nice applications, real applications. And here I want to show you, this is one project we did. We developed an app for food recognition, and we collaborated here with Medical University of Groningen from the Netherlands and with Nestle from Switzerland. And in this lab, in fact, it is designed to help patients with kidney transplant, because for patients with kidney transplant, following the right diet is very important to reduce the probability to reject a new organ. And this is really very, very important for these people. So this is an European project where we applied our problems. And this is another project where we were collaborating with another company. This company is called Green Habit, and the founder of the company is Chantal Linder. She has a very nice TED talk about how to manage the monster in your head. So she was a very promising sport woman, but she got a very hard, very heavy injury, and when she was young. So her future changed very much, and there was no way to get better and better. And finally, she discovered that using the right nutrition and in a proper combination with other elements, as you see, exercise, relaxation, positivity, and social environment, you can improve your well-being. And this is a real story. You can go and look at the TED Talk. It's very nice. So in this case, we applied in this serious game she created. We applied also our algorithms for food recognition. And last but not least, here I see a lot of young people. What I like very much is that all this work also opens a lot of opportunities, professional opportunities for young people. And here in this picture, you can see the guy on the left, Mark Bolaños. He finished his PhD in our group 3 years ago, and he developed a lot of food recognition algorithms. And in fact, he was creating also this app for the kidney transplant patients. And also he created this smart kiosk for the self-catering restaurants, so that you put the tray, automatically recognize the food, and you get the ticket. And then he decided to go forward with the company, with the startup company, and at this moment he is working on it. So to finish, so what is my message is that food recognition and food image analysis is a perfect test domain for powerful machine deep learning models. Food image analysis is highly underexplored, a lot of opportunities for research, but also for technology transfers. And this is my feeling that, and that's why I also call you, because our community, the community of people working on food image analysis, could play the same role as the community did 25, 30 years ago on face image analysis, because it is a perfect benchmark for computer vision and deep learning algorithms. And taking into account that data are really very complex, well, so data-centric food computing is really something that we really need to think about if we want to get some promising, well-performing models. So multiple computer vision problems are highly relevant for food image analysis, as I mentioned here. Uncertainty modeling, transfer learning as multitask learning, and self-supervised learning, vision language models, fine-grained recognition, multi-scale classification, etc., and multiple reapplication and professional opportunities are here, especially for people thinking about what. So all this cannot be done without the work, the hard work of all these young people, where I'm very happy to work with. And but we like to have good work, but also we like to have good life. So you see, not always work. Thank you very much.
We are open for questions. We have 10 minutes, then we can do our next presentation.
Thank you so much for the talk. That was amazing. I had one question related to the volume estimation.
Yeah.
Which you mentioned. You showed the results on the nutrition 5K data set.
Yeah.
But I'm wondering how exactly you compare your results, because most data sets don't have like volume information.
Yeah, it's true that the Nutrition 5K, they are not giving exactly, well, they give a guide how to compute the volume, but they are not publishing exactly the volume. So what we do is, it's a little bit tricky. That's why also we created our data set in order to see the results, right? But later Ahmad will be when we speak about the challenge, so you can also talk to him, and he will be very happy to go into the details. Yeah. But this is one of the big problems, that we don't have real meshes. So we are also thinking about, we created our data set that we should publish soon, 20 food categories also, and also we are looking for other data set that not necessarily are on food, because we don't have ground truth. This is a big problem. Yeah. Yeah.
For the ontology method that you showed, where you assigned like a bunch of how similar images to a bunch of different categories, what are the categories that you're using there?
What are the categories?
Yeah.
Well, in this case, okay. This is the, like, for example, here, this one.
No, I think it was a little bit further along. Yeah, right here. I think in the next slide there was like a yeah, right here, the relationship matrix. What
Yeah.
are the what's the relationship matrix they're comparing?
So here the idea is to relate food concepts, and these food concepts could be anything, right? We did it before, multitask learning. That is one simple way would be, as it is in the picture, that is you relate dishes to the food groups. But the idea is to go much more general and relate each concept to each concept, because what we found is that in food concepts, you don't have a strict hierarchy. For example, mayonnaise. Mayonnaise is food, is sauce. Ketchup is food or sauce. Maybe for something is ingredient, right? For Russian salad, it is ingredient, but for others, it's like sauce. So there is a lot of ambiguity in when you categorize the food concept. So the idea is to go more general and to have here concept to concept. This is the idea.
And the concept of something like sauce or
sauces. It could be sauces, it could be action, it could be food category like pasta, rice, vegetable. It could be dish like canard. It could be whatever. Right. Yeah.
Very nice talk. Thank you. So I think you showed a lot of different data sets people are putting together, and then with different components and so on. And then I think the nice, very nice analogy to looking at solving face detection problems, right? So along that line of thoughts, what do you think are some of the important component that should go into data set that for food image analysis? Because I would sort of argue that face maybe is an easier problem because analytically, right? Because everybody, we are genetically designed to have a certain features that are across different, race and so on that are there, right? So for example, you are looking at certain, key points, etc., that we all have eyes, nose, and mouth, right?
Yeah.
But that is not necessarily true for the foods, right? And I think the food analysis is a much complex problem because food recognition is part of it, but there's many other things that we're also interested, right? So I think coming up with good data set is very important for the community because then we all have something that we can benchmark on.
Right.
So right now, I think there are data set that one data set may satisfy, one goal of looking at recognition because you have a lot of categories and a lot of sample, but there may be another data that are good for other things, looking at, 360 views and so on. So what do you have any thoughts along the line of how, the community can sort of work together for, creating these data sets that will be good for benchmarking, different things that we want to do in this domain?
Yeah.
And
And is our next talk will be the first oral by Jesus. Are you online?
Yes, I am. Can you hear me?
Yes. Can you share and then you can start?
Okay.
Uh,
Can you see my
uh,
screen?
Seconds. Okay. We can wait. It went black.
Now?
Now it's good.
Okay,
Yes.
perfect.
You can start. Thank you.
Thank you. Hello everyone. My name is Jesus Molina Rodriguez de Vera, and I am a PhD student at the University of Barcelona under the supervision of Professor Petia Radeva. Today I will present our last paper, Lo-Fi, Long-Tail Fine-Grained Network for Food Recognition. In today's presentation, we will first introduce the problem at hand, that is, food recognition, as well as the main challenges that we face when dealing with it. After that, we will present Lo-Fi, our proposal to address and overcome these challenges. Then, we will present our results in some benchmarks, comparing with the state-of-the-art solutions and updating the different elements of Lo-Fi. We will finish the presentation with some conclusion of this research and some promising next steps. I think that all the audience here is aware of the importance of food, not only for the human health, but also for economy and sustainable development. Therefore, I will skip the motivation for food computing in general and pay attention to our particular task. As the name of the paper suggests, we focus on the problem of food recognition. With food recognition, we refer to a task of locating and classifying the different food items present in an image. This can be done in two ways: by finding the bounding boxes, that is object detection, or by finding the accurate masks of each item, that is instance segmentation. This task of food recognition presents some critical challenges, among which we highlight three. First, the presence of fine-grained classes. This is an issue common to almost all food computing problems dealing with different dishes or ingredients. This challenge is caused by the presence of groups of classes that are very similar to each other. This, in turn, makes it very difficult for the model to distinguish them, being a potential source of mistakes. Second, food object detection and instance segmentation datasets present a very pronounced long-tail distribution. In classification tasks, a long-tail distribution refers to the phenomenon where a few classes have a large number of samples, while the majority of classes have significantly fewer, posing challenges in training models to recognize these less represented categories effectively. Third, food dishes usually present visually complex layouts. These complexities are due to different factors, such as the lack of a regular grid, non-uniform shapes, highly variable overlap, or ingredient scale. This makes the localization of the food items in the image very hard for general domain object detection systems. Once we have identified the challenges, we can move on to the presentation of our proposal to solve them. Our proposal, Lo-Fi, is built on top of two-stage object detection or instance segmentation networks. Although it can act as a universal add-on to any of these networks, here we show a masked CNN for simplicity. The region proposal part, this part, is kept untouched, and we focus only on what happens once the feature vectors of each region proposal have been extracted. We represent them here with green cubes. So from that point, we perform a series of changes to architecture to tackle the previously mentioned challenges. In order to deal with the fine-grained nature of the data, we propose a multitask framework for fine-grained classification. Given the long-tail distribution of the categories, we perform some changes in the classification branch of the network to improve its robustness against high imbalance. Regarding the visually complex layout, we address it from two perspectives. First, we perform some smart replacements in the regression and segmentation branches. And finally, we add a graph neural network-based module to further post-process and refine the detections of the network. Let's start with the framework for fine-grained classification, which is represented by the dashed red box. So as we mentioned earlier, we want to help the network to distinguish similar categories. The first step is to identify groups of confusing classes. To do that, we rely on lexical information. We take the labels existing in the dataset and using a text encoder, compute the lexical embedding of each class. In this latent space, we compute the cosine similarity between the different embeddings of the different categories. Once we've done this, it's possible to apply any clustering algorithm in order to find groups of classes with similar embeddings. We will consider those clusters as the groups of potentially difficult to distinguish categories. In the case of lo-fi, we use hierarchical agglomerative clustering to find them. For each one of the identified clusters, we add a linear layer in charge of identifying the elements of that cluster. These heads receive as input the same feature vector that we are using for the global classification and regression heads. And it's important to know that each feature vector is fed to all the subheads, not only to that of each particular cluster. Because of that, apart from having one output for each one of the classes, we have an additional other output to indicate that a feature vector does not belong to any class in this cluster. These heads are trained using cross-entropy laws, and we simply aggregate and average the values of each one of them and add it to the total training loss. These new tasks provide additional guidance during training and force the network to learn features that are more helpful in distinguishing similar classes. However, we don't use their outputs in inference. Therefore, as we can see here with the black arrows, computation does not flow to these heads during inference, making the approach very cost-effective. Let's continue with the changes applied to deal with the long-tail distribution of the data. All these changes only affect the classification branch of the RCNN. Two main improvements are introduced. You can see the references of these improvements in the bottom of the slide. First, we replace the last classification linear layer by a norm linear layer. What this is basically doing is replacing the traditional dot product applied to compute the per class logits with a class-wise cosine similarity computation. In this way, what really matters is the direction of the learned class vectors and not its magnitude. This is key in fighting the effects of class imbalance, because the magnitude of the learned class vectors is usually higher for more frequent classes, leading to frequent classes being easier to predict regardless of the direction of the latents. On the other hand, we modify the classification loss and use the equalization loss version 2 instead of the traditional cross-entropy loss. The equalization loss automatically weights the magnitude of the gradients based on the dynamically compute frequency of the different categories. Thanks to this, it reduces the impact of class imbalance during training. The next component of lo-fi affects the regression and segmentation heads of the RCNN. Regarding the segmentation head and the masking, instead of using the vanilla segmentation head, we use a mask scoring head. This adds an additional head to predict the intersection over union of the generated mask with the ground truth. This self-assessment of the quality of the output by the network itself helps to increase the quality of the predictions. In terms of the regression branch, what we do is replace the loss by the generalized intersection over union loss. This loss, here you have the expression, provides a more informative gradient for bounding box regression by incorporating special relationships between predicted and ground truth boxes, leading to a better convergence and performance, especially in cases of non-overlapping boxes. Last but not least, the graph confidence propagation module, here with the dashed blue line, serves the purpose of refining the outputs of the network. We'll first motivate the need of this component. Let's consider the image of this cup of coffee that I show here. And as we can see, we have one prediction for tea, one for decaf, and 3 for coffee. The numbers between brackets represent the confidence of the network on that particular prediction. In vanilla RCNN with normal non-maximum suppression, we will pick decaf since it has the highest confidence. However, one might wonder if the presence of 3 predictions for coffee should make this a preferred option. Instead of setting up a heuristic to make this decision, we decided to look for a learnable solution which enabled us to combine information from all these predictions and further refine them to lead to a better output. In order to do that, we make use of graph neural networks. Using the feature vectors of each prediction as the nodes of a graph and the information about the relative position of the boxes to build the edges, we create a graph which captures the whole output of the network and the relation between the different detections. Then we feed this graph to a trainable graph attention network, obtaining a refined feature vector for each prediction. Here we represent these new refined vectors with blue instead of red. For each one of these refined vectors, we can perform a new classification and regression. These heads are trained with the previously explained losses and are training along with the rest of the network. Thanks to this component, we can train the network to combine the information from these neighboring detections to create better predictions. If we visit one last time the final diagram, we can see how the original classification and regression heads are used only to guide the training, and they are ignored during the inference. We represent this, remember, with the black arrows. The final output at test time is that of the graph confidence propagation network. With this, we have completed the picture of our proposal lo-fi. Once we have understood how it works, let's visit some of the results present in our paper. In this slide, we can see a comparison of lo-fi with different methods of comparable size from the state of the art in general domain object detection and instance segmentation. We present results for two datasets, one for food object detection and one for food instance segmentation. As we can see, lo-fi clearly surpasses all the considered methods by more than 4 and 2 points in mean average precision, respectively. This proves that lo-fi successfully addresses the particular challenges of food recognition. We also update the different components of lo-fi to better understand how they contribute to the increasing performance. Here we have SR for smart replacement in the main classification, regression, and segmentation heads, FG for the fine-grained module, and GCP for the graph confidence propagation component. We can see that the addition of the different modules always leads to improvements in both datasets, indicating that all the components of lo-fi are important to achieve the best performance. For more insights on how the different components affect the actual prediction and more details, we have a more detailed analysis that can be found in the main text of the paper. Despite the promising results, there are some limitations that cannot be ignored. First of all, we depend on the quality of the text encoder in order to find good groups of similar food. Therefore, if we are dealing with ingredients in a language without a good enough text encoder, it will be impossible to use the proposed fine-grained module. Secondly, the information fed to the graph neural network for the graph confidence propagation component is very limited, and we could expect that further exploration of this technology could lead to even larger improvements. And finally, since we have increased the number of components in the final training loss, the hyperparameter search space increases considerably. Although we obtain the reported results without any tuning, extensive testing might be needed to get the optimal performance. To finish, let's recap the main conclusions of this presentation and propose some promising next steps. In this paper, we introduced lo-fi, a two-stage food recognition approach tailored for the particular challenges of food. As we have seen, focusing on these challenges have led to a method that is able to outperform state-of-the-art general domain solutions. The two main contributions of our work are the efficient usage of cross-modal information for the task of fine-grained food recognition, as well as the smart and learnable combination of neighboring detections through graph neural networks. The next steps that we envision are linked to the previously found limitations. First of all, we think that we will use more advanced language models, such as large language models. Also, we could investigate more in detail the usage of graph neural networks and add more information apart from the one that we are using right now. And finally, we think that it's important to test our solution in real-world scenarios. Since the datasets that we are using are relatively small, it's important to test in a real application in order to get a better idea of the potential of the solution. And that's all from my side. Thank you very much for your attention. And in case you have any question, please feel free to ask now or contact me later.
Thank you. So we are now open for questions. Are there any questions from the audience? So I have a question. So in terms of the hierarchical fine-grained representation, do you treat all the class the same? Do you think that because there's hierarchical representation, then some weights need to add to different level of details in terms of class representation.
Yeah, well, it's true that with our current approach of using hierarchical clustering, we are limited to have every label in one group and only one group. And it's true that it might exist the case in which we same class might be confused with more than two groups, but it's a path that we have not explored yet.
Okay.
So is there any question from the online participant? Okay, so if so, let's thanks the presentation.
Yeah.
So for the next part of this workshop from 10 to 11 is the coffee break and poster session. So all the posters are in the fourth floor, the exhibit hall 4E. So for this workshop, we are in the poster number from 136 to 148. So so you can take a break and to visit the poster board, and I will see everyone back in 11 in this room. Thank you.
Okay, I think we all know that it's difficult to remember what we eat, right? But we know that food is important. I mean, it's the basic element for our body, for our health. So just want to make the statement that food logging is the very basic step and it's very important for healthcare. Yeah. Today we got large language model. Indeed, we can do something even beyond food recognition. So I would like to start with this picture you may know. So it's a paper published 10 years ago in CVPR by Austin Meyer. So he gives the picture of what we should do in this area. So well, we start with detection and classification of the food in an image. Yeah. So an image may have multiple food, as I saw some of you doing this during the poster section just now. So I do the food segmentation, yeah, to localize the food. We may also try to analyze the attributes, for example, how the food is prepared. For example, it's deep fried, it's boiled. Okay. There may be repeated food in the image, so we also do accounting. So all those together, right, tell us the content of the food, but that's not enough because we also want to know how much food we consume. So from the 2D image, we want to estimate the depth. That's why we have the depth map, and then we do the portion size estimation. With all this sort of like, we complete the picture, we have all the major information, we can use this for nutrition estimation. This is basically what we want to do. Then I would like to give a very brief summary of what's happening like in the past few years. So ingredient recognition has been proposed like a few years ago, and then there's a data set constructed for more than 300 ingredients. So this is the picture in the data set. So the idea is basically to recognize the cucumber, carrot in the image. So I believe you can see that this is a very challenging problem. So a year later, somebody proposed the idea of instead of address this using a classification approach, why don't we just make it a retrieval problem? So we retrieve the recipe of the food image, then we extract the ingredients from the recipe as a result of recognition. And there are a lot of work in this area. Most of the work basically assume one food per image. That's definitely not true. So later, there are more work about food segmentation, including instant segmentation. For example, this is a popular Asian food. Yeah. So if you never eat the food before, maybe you also have problem like how to segment the food. Yeah. So that's challenge about food segmentation. And then later on, right, gun become popular. For example, in CVPR, almost all papers are about gun in some of the years. Yeah. So this is the example of using cook gun to generate the image from the recipe. And on the right is a graph showing the cooking process with all the cooking action and ingredients. And the graph is estimated from an image, which is very challenging. Yeah. Then after 2020, then people start to pay attention or recapture this problem of portion size estimation, which is really challenging problems. So this is an example that on the left, we have the sample image with the calorie information, with the nutrition information label on the image. On the left, on the right, we have the depth image. We all agree that, like, maybe at the end of year 2022, there's a big jump in technology because of large language model. So today, indeed, we can do something like, you can ask like, which item in the breakfast is rich of protein, and then you could segment the item, in this case is the egg, and give you some information about why it's rich in protein. So that's possible. So all these are basically sort of like our good effort in the past, you can say in the past 10 years. Then you may ask, what should we do today or in the near future? So we have large language model, which sort of like has the capability of doing reasoning. So given a food image, well, I believe we should reconsider this problem of nutrition and calorie estimation. Yeah, because we can do reasoning. If you do this task well, we can use it for QA tasks. For example, we can have a question like whether this dish is rich of protein or containing too many saturated fat, for example. We can even think further. For example, can I replace the ingredient in this dish that may cause my food allergy? Something like this, yeah. And then, well, today's AI is generative AI. So we should be able to do tasks like show me the recipe of how to prepare the dish, something like this, yeah. So this is about LLM basically doing analysis on only one image, yeah. So I believe in long terms, what we want LLM to do is not only one image, but our food log. That means a series of images over a period of time. If this is possible, then we may be able to do something like asking the LLM to provide or to recommend the food that we should eat or the food that we should avoid, for example. So this is about preventive healthcare. We may be able to ask LLM to predict our future health, or even like ask LLM the question like, how am I going to look like in the next 5 years if I continue eating the food, or it change my habit to eat other food? How would I be look like in the future? Something like this. So in short, with LLM, maybe you can start to think about like how to connect food recognition and healthcare, yeah, to do something like dietary advice, recommendation, intervention, and so on. Yeah. So basically my talk today, right? So I will give a very brief introduction about the progress made in food computing or food recognition. I will talk a bit about my recent work on food large multimodal. Yeah. Then if time allows, I will share with you some of the challenging we face when we develop the real system. Okay, so this is one of the network, I would say in the early year for food recognition. So it's basically just a simple convolutional networks, but with two branches. One branch for recognizing the food, the other branch for recognizing the ingredient. Today we look back, it's really a very simple neural network. So this convolution networks has been extended to recognize not only ingredients, but also other elements like how a food is cooked, how a food is cut. Yeah, I believe you can imagine that this problem is really challenging. Yeah, so when we try this problem, the accuracy is really low. So very quickly, people start asking, instead of like treating this as a classification problem, we should treat it as a retrieval problem. That means retrieve the recipe of the image. Then the problem becomes cross-modal retrieval. We all know the key idea is basically learning the joint space between image and text. Then you can use the feature like given the image, you retrieve the recipe. Given the recipe, we retrieve the image. Yeah, something like this. So recipe is really rich of all kind of information. The title gives us a lot about like what kind of food it is about. Yeah, we have the sample image, we have the ingredients. Not only the ingredients, but also the unit of each ingredient as well as the weight of each ingredient. Then we have the cooking instruction. Cooking instruction indeed tells us a lot of information. Cooking action, the location, the time, the process, and other information, including the taste, the temperature, and so on. So the question is, if we can retrieve the recipe, then maybe we can do something. Okay, so this problem, so-called this image to recipe retrieval, right? In the past few years, there are a lot of papers on this topics. Then this is a very classic architecture for this problem. The focus is basically how to encode or how to capture the information in the recipe. So that's one of the early work which use bidirectional LSTM to capture the ingredients, because the ingredient is not, I mean, sort of like there's no time sequence, so basically using bidirectional to capture the ingredient information, and then use hierarchical LSTM to capture the cooking instruction. Okay, maybe you have seen this network before, it's quite popular. And then there are other more advanced network based on this. HT, hierarchical transformer, is one of the good example which produce quite good result. So the basic idea is basically just replace all the LSTM with transformer. So we have a transformer for title, for ingredient, for instruction. Other than this, there's a loss function on the top. You can see REC. REC is actually a self-supervision loss. Basically, you want to learn the embedding such that title embedding is similar to ingredient embedding, ingredient embedding is similar to instruction embedding, and so on. Yeah. So I think today is right. A lot of people are using this architecture to encode the information in the recipe. There's another work. MetaFood is also doing something like this, but using a large visual language model. For example, image encoder is based on clip, for example. And then they also do something similar to BRIC. The MMR is so-called, they want to model the interaction between text and visual, but using loss function similar to BRIC to do this. So this is also one of the paper or architecture that give very good result on these problems. So no matter which architecture being used, okay, the key idea is basically trying to learn the joint space or trying to learn the representation across different modality. So that's the on the bottom, the equation is sort of like the standard similarity measure, which we embed the recipe and then embed the image and then measure their cosine similarity. So the question in my lab is trying to sort of like looking at this problem is, we have the recipe, which has a lot of information. We have the image, may have some information, but maybe not everything, or some of the information is not nicely captured. For example, ingredient are like hardly visible or occluded orders. So we ask the question, when we learn this cross-modal alignments, right? Are we trying to learn the correlation or learn the cause and effect relationship between two different modalities? Give a simple example. What makes this image as the Thai beef salad? So I show three pictures here. Okay. On the left, the one is Vietnamese beef salad. In the middle is Cambodia beef salad. On your left, this one is so-called, I'm not very sure, American style beef salad. So what makes us to know that given this image, then the right recipe should be Thai beef salad, but not other kind of beef salads. So that's the question we ask. Yeah. So we're trying to like do something on this. Then we sort of like refer to causal theory that you may have known and come up with this graph. We call it as a causal graph. So basically we say for recipe representation and for image representation, ingredients are the key component. Yeah. On the other hand, when we try to do the cross-modal learnings, right, the image representation is trying to learn something from recipe representation because recipe has more information. So as a result, based on this causal graph, we say, well, the ingredient actually has double effect on image representation, or in other words, ingredient becomes the co-founder. So we try to do the intervention by removing the edges from the image. So we have this graph. Then we go through the process. You may have known the backdoor adjustment. So we follow the step, go through the do calculus, and then we come up with this formula at the end. So you just need to pay attention to the one I underlined, and then compare to the image representation or embedding. The terms that we add in after the derivation is basically this part. That means the image embedding, right, very often is sort of incomplete. If you look at the causal graph, right, because of the co-founder, our conclusion is that the representation learning emphasize too much on dominant ingredient. For example, in the previous example, he may emphasize beef a lot, but other minor ingredient not so much. Yeah. So this formula sort of like giving the message that we need to pay attention to image embedding in the sense that we need to add back some of the ingredient that may be overlooked during the representation learning. Yeah. So that's the key message. So based on this formulas, right, then we implement something on top of this standard cross-modal retrieval things. So on the bottom right, we call it as a debiasing module. We have two parts. One part is basically predict the ingredients. Predict the ingredient from the image representation. On the other hand, we learn a dictionary. Like every ingredient, we have the embedding. So once we predict the ingredients, then we retrieve the ingredient embedding from the dictionary. We add back to the image embedding. Then the network is trained end-to-end. So at the end, we hope the image embedding becomes something more powerful. That's our hope. Yeah. So with this, right, we also think about a related question. Like a lot of people are working on this problem, image to recipe retrieval. Indeed, we do know how much performance we can reach. That means the upper bound performance that we could have. So when we think about this problem, right, then we said, why don't we do a simulation? Answer this question. How good is retrieval performance by simply matching the predicted ingredient with the recipe? So this is basically a classification approach. We predict the ingredient from the image and then match against the recipe. So simple text matching. Yeah. So we do the simulation. So you look at the figure on the X, it's basically classification accuracy, top one classification accuracy. On the Y-axis is recall at one. It means you only look at the top one. Basically, it's the accuracy, top one accuracy. So if you look at this graph, right, basically means if the accuracy of ingredient recognition is like below 20, nothing can be done because you cannot differentiate the recipe in the data sets. By the way, when we do the simulation, we do it on recipe 1M and using all the test set, which is 50K, which is quite huge data set considered for this problem. Yeah. So if the accuracy reach 50%, then you can reach the recall at one of 20%. Is this considered good? Well, you look at one of the best performance by HT. So it's actually already better. Yeah. So HT is by using embedding techniques. Yeah. Then the orange curve is basically just by matching the ingredient with the recipe. Yeah. When we try to do the same simulation with the causal theory, the formula I show you, the result is even better because kind of like we call it with the bias the representation. For example, at the accuracy of 20% to recognize the ingredient, we can reach recall at one at more than 40%, which is quite impressive. Then we project all the methods, all the best methods for this problem, including T-Food, VLP Cook. Yeah. So far as we know, this is the best result. Yeah. So you could see that, basically you could see that first, the motivation of using embedding approach, the blue curve, yeah, is much better than simple text matching, because text match, by using text matching, you need to guarantee relatively high accuracy for ingredient recognition, compared with embedding, right? For example, 20% of recognition accuracy is already allows us to reach kind of like 40% of recall at one. Then what is the upper bound performance? So if we really can make ingredient recognition to 100%, then I would say the problem is kind of like almost solved. So recall at one is more than 95%. Yeah. Okay, hope this gives you some picture about this problem. Okay, so I talked about ingredient recognition and then recipe retrieval, right? Then we do have the problem of segmentation, which I saw some poster about this topic. Then this is actually the work by Prof. Rita, which is one of the first paper about food segmentation. We know that YOLO used to give us a lot of bounding box, yeah. So you need to have some post-processing. So another branch is food segmentation, basically applying fully convolutional network to segment the food region, and then combine these two, like to do the pruning, reduce the number of repeated bounding box orders, and finally get some good result. So this is one of the first work about food segmentation. So there are other work which, like this one, sort of like extending segmentation to counting and do this together. So it's basically like a multi-task learning with 3 branches. One branch for duration CNN to do the counting. The second branch is sort of like semantic segmentation, but the result of segmentation is basically focused on the center part of the food item. Yeah. And then there's a sibling detection there. It's basically to explore the pixel connectivity, then extend the result of semantic map to come up with this instant segmentation. Yeah. And then I could show you some of the result. So this is actually done by PhD student. He tried different network about image segmentation, and then those are the few network showing reasonably good result. Not all network can work on food. We know about this. Okay, so the first example is the picture with a lot of occlusion. Yeah, so that's the result. On the right hand side, sibling network is all result. And then another example with the food stacking on each other. Yeah. Then the food item with not so clear boundary, even though there's 4 food items. And then the food on some clutter or noisy background. Then the food with some perspective distortion. Yeah. So at least you can feel like the challenge of this problem. So just now in the poster section, right? Some of you asked for data sets, right? Indeed, all those data sets are in public domain. Yeah, if you want, just let me know. Yeah, indeed, we have more data sets, some of which we cannot announce because those data sets, those images are come from government, Singapore government. We are not able to release the data set. Okay, so my student also extend this work into a real-time system for counting, segmentation, and recognition. The key idea is actually this one. The semantic space is actually learned from the fully convolutional network. And then he make it real-time in the sense that he only use this semantic space. That means one network for counting, for semantic segmentation, and for instant segmentation. Yeah. So you see the food counting, semantic segmentation, and the food instant map. Yeah. Then to create the final result, we simply use some post-processing techniques, a bit engineering, and then come up with the result. So it's basically we able to sort of like classify each of the item in the food, as well as like counting the item. For example, fried fish is labeled as item 3 to 6 fried fish, something like this. Yeah. So just to give you some sense about what I mean by real time. So in the system, right, we able to like within 1 second, we able to process like around 40 images. Yeah. So the red star on the end. Then you can refer to Euro because most of us know Euro. So Euro is the blue one, basically this one. Yeah. So you can sort of like get a sense about the techniques that we propose. We call it as food mask. It's basically faster than Euro, as well as provide better segmentation qualities. Okay, so that's some of the result. I think I mentioned to some of you like the first picture, right? So this is the typical food in Singapore, in Malaysia, or in Southeast Asia. So it's quite challenging to segment the dish on the plate, something like this. Yeah. So again, we have the data set. Yeah, the data set, for example, the data set on the first row is basically collected from the canteen in the university. Yeah, so we have quite a few of those data sets. Okay, we also do ingredient segmentation. So this is one of the data set that some of you use, food set 103. Yeah, so you can see that the problem is actually more challenging than instant segmentation, depending on how you define instant. So instant here is defined as the ingredient. So if you look at the image on the right, I mean this one, yeah, this one, then you could see that it's basically quite challenging in the sense that you not only recognize the dish, but you need to extract the region correspond to onion, carrot, tofu, and so on, which is very challenging. Yeah, indeed, we know it's very challenging. It's almost impossible to get a good result. The problem we ask ourselves is it possible to label so many segmentation masks for ingredient recognition segmentation? It's almost impossible. Yeah. So that's why we come up with this idea of open vocabulary ingredient segmentation. The idea is basically we have large language model, right? Can we just use a small, don't say small, okay, enough amount of training example, and then for those ingredients that are not in our training example, we can still do the segmentation. So that's the idea. So basically, we train, we call it food image encoder, which we call it food learner. So this food learner is trained by using recipe 1M dataset. We only use the image level ingredient feature. That means we don't know the segmentation about the ingredient. We basically just use the image label and to learn a large language model similar to BLIPS. Yeah. So food learner is kind of like a large language model specifically for food. So once we learn the model, right, then we use it to augment. Next one, we use it to augment the text encoder, for example, clip encoder. So when we have the prompt input to the clip, it will generate the text embedding. Then we have another branch which take the input from the image. In other words, the user basically give the image, give a list of prompt about the ingredient they want to segment. All this enter into the so-called image informed text encoder. Then we produce the text embedding, and then use this text embedding directly compare the similarity with every pixel in the image and come up with the segmentation result. Of course, this is not our result. This is ground truth, because the real result is much worse than this. Yeah. So this paper will be presented tomorrow. Yeah. If you'd like to know, then welcome to my poster. Yeah. Okay. So that's about food segmentation. Nutrition estimation for me is one, I would say, the most challenging problem in food recognition. So if you know the ingredient, if you know the weight of every ingredient, if we know the food density, which we know, yeah, then combining all this, we can estimate the nutrition. So the challenging part about this is basically, how do you recognize all the ingredients, segment all the ingredients, and knowing their weight? So knowing their weight is even harder, in my opinion. So I don't have good knowledge like how to present this topic. Just list out some topics. For example, their work, for example, in nutrition 5K, using 2D direct estimation. You pump the image into the model. You hope that the model will give you the result. Yeah, which is basically the best result we have so far. The right way to do this, of course, is use the depth image. Yeah, the even right way to do this is basically construct the volume, but it's really challenging, especially you consider to construct the volume for all kind of food. It's even challenging. So the next is should be more kind of like classic approach. You do the 2D image segmentation. Of course, you can do it on 3D image segmentation. Then you count the pixel. Then offline, you learn the correlation between the pixel and the calorie or nutrition information. Something like this, yeah. So quite a few papers is actually following this approach. Another way is just using recipe. Extract the information from recipe and then do the estimation. Of course, it's not really a good way to do this, simply because who knows, we may not follow the recipe correctly, right? Yeah. So that's another issue. Okay, I hope all this give you some sense about different topics in food recognition, but just to warn you that it's impossible to treat all the food equally. For example, those are food, in my opinion, easy to segment, easy to retrieve, easy to count. Japanese food is good in the sense because they put the food into small bowl. Each of the bowl has a standard. No, any Japanese here, they follow everything, right? The bowl must have standard, so I would say it's easy to segment. Easy to segment and then to quantify. For Chinese food like this, right? Well, who care about counting? Yeah, counting how many peanuts is impossible, right? Quantify, maybe, yeah, but if you want to segment every ingredient in the image, it's almost impossible. So this is the Malay food in Southeast Asia. I would say it's even harder, yeah, because everything is with curry, similar color, even though with different ingredient, yeah. So sometimes we are saying that the hardest food to recognize in the world is Indian food and Malay food, yeah, because they all have similar color. Okay, so next I will talk a bit about the large multimodal model that we try to build. So this work is together with Fudan University, between Fudan University and Singapore Management University. Yeah. So what we want to do is basically build a large language model that sort of like integrate different tasks I listed here, from food classification to ingredient recognition to recipe generation, nutrition estimation, food segmentation, and food dialogue, all this. We're trying to do something on this. So what we do, I would say indeed, today is very standard. Everybody is doing this, except we do it on food. So given the query, given the picture, we input to the RAWA, and then vision encoder is clip. Okay, we input to the large language model and we do fine tuning. Okay, so first we treat the food classification, ingredient recognition, recipe generation as the vision QA task. Okay, so it's basically asking what is this food, then you will answer what's the ingredient and so on. Yeah. Then the second group of tasks is nutrition and calorie estimation. So what we do is basically we create the new token from the existing vocabulary in the large language model. Those tokens include calorie. So you see the terms in the bracket: calorie, fat, carb, and then protein, and so on. So we basically create this new token. For each of these tokens, right, there's a corresponding embedding in the large language model. So we just extract those value, build our small or mini neural network for the recognition of value. So at the bottom is basically each color represent either calorie estimation, weight estimation, or nutrition effect estimation. So that's what we do. Yeah. Then we also do something on food segmentation. Similarly, we create new token called set1, set2 correspond to which. So the user may want to do the segmentation of particular food or want to do segmentation of multiple food. Yeah, so we create different set tokens. And then similarly, for each of the embedding correspond to the token, we feed them to visual encoder. The visual encoder here, at this moment, what we use is SAM. I hope in the near future, we can use one of the process SAM for food in here. Yeah, and then do the segmentation. Okay, so that's what we did. Next, I will briefly explain how we train the network. It's actually very straightforward. Okay, the first thing we do is basically we treat all the following tasks as a multi-task learning. Okay, so we use the existing data set, for example, viral food in my labs, and then recipe 1M, nutrition 5K, all this. Okay, we do multi-task learning and then finish the first step. The only thing that need to be clear probably is the loss function creation of the new token. They are quite straightforward. The second stage is basically once we train the basic function, the second step is we try to generate the conversation. So what we do for multi-round conversation is we use the nutrition 5K. So you have the video, you have the calorie, all kind of labels, right? We use this to instruct GPT-4 to generate conversation. Then we classify the conversation into different topics about nutrition, calories, about health and disease, metabolism, and so on. Okay. So I have one example there. So it's basically user asking, all those are from chat, from the GPT-4. User is asking like, can you provide the nutrition information about this picture? So because we have nutrition 5K, which have all the information, so this helps us to guide the conversation. Yeah, and then the agent will just list out all the number, okay, calorie, nutrition, all this. Then the user can further ask how to improve the dish, make it more healthy. Then the agent, in this example, the agent said less cheese, put some vegetable, there are some rice there. Yeah, so instead of using white rice, you ask the user, maybe he or she can use brown rice, for example. Some of this, yeah. So I would say we try to use nutrition 5K to do this. Yeah. Some of the response from GPT-4 looks reasonable. Some may have error, and then we don't have chance to really look at all those examples to correct them. So what we do is basically we do a user study, sort of like we understand how good or how bad the result is. That's it. So for segmentation, right? So reasoning segmentation is basically not just segmentation, but segmentation that requires some reasoning. Yeah. So we use foodset 103, which has the label to instruct GPT-4 to generate the conversation. So the example I listed there, for example, we ask which ingredient in this dish is high protein, which ingredient may help lower the blood pressure or those. Okay. So we kind of like asking GPT-4 to come up with this kind of question and with the conversation. So so it's very simple, right? We LLM life becomes simple. Yeah, we to enjoy food. Yeah, hopefully. Yeah. Okay. So I will give a very quick review of the performance. Okay. Some of the result here I would say is cherry pick because people may share the performance from different aspects. Yeah. Then we pick some of which we can show the difference. Yeah. So for food classification, right, we compare to food 101, and then we compare to the result published in the PAMI. last year by the group from China, Su Qiang's group. Yeah, so the result is a bit better. Then for recipe generation, right, we use recipe 1M as the test bed. Then we compare with a paper called Fire, you may know. So Fire is basically using bricks and VIT to generate the recipe. Yeah, so our model is actually sort of like generate much better performance than Fire. Yeah, but frankly speaking, I would say there's a big room to improve the performance because kind of like it suffer a lot from hallucination issue. Yeah. Okay, then we also do the ingredient recognition. I think so we compared to the result in the PAMI paper published last year by Su Qiang. Yeah, so we also get some improvement. Then for segmentation, we compare to another large language model called Lisa. Yeah, so we also get a much better result from them. So one of the reasons is Lisa is a general purpose large language model. We don't do any fine tuning, but our model is built for food. That's why the performance looks much better. Then nutrition 5K, we did pick the best result from the nutrition 5K or the relevant paper, in the sense that the best result is based on 2D image estimation. Then when we do it on the on our model, we get a slight improvement. So this is MAE. So the smaller value means it's better. Yeah. So hopefully this gives you some sense about the performance. Okay. If you want, you can get the data set from here. But just want to warn you, the food dialogue and food reasoning segmentation is not perfect. We don't have time to correct all the error. We only do a user study to give like a reader or user like you some hints about how good or how bad it is. Yeah. Okay. So finally, I think I will spend maybe a few minutes to talk about the system we do. So you may have heard about this food AI developed in Singapore Management University, sort of like many years ago. So we start from the 101 food classes. Is actually local food. Okay. We collect more than 200,000 images, labeling, developing the convolutional network for this. So we get the very good accuracy. Top 5 is 97. And then food AI has been used by Singapore Health Promotion Board. We have a lot of data from this Singapore government agency, which we are not able to release the image, which we just use it for like our own study. And then we also work with medical school in National University of Singapore and some of the startup company like Embody that you may have heard about. BizWoo is a local company in Singapore. So over the years, right, we have built our own data set. Again, we are not able to release the data set somehow. Largest known is a few years ago. Yeah, forget about this. Of course, it's not the largest. Yeah, so we have like 756 visual categories. Visual categories is not really the food categories. We indeed have more than 1,000 food categories. We just merge those visually similar ones as visual categories. So one of the problems that we face is actually this long tail distribution. That has a paper just now also about this issue. Yeah. So I also have students trying to work on this long tail distribution problems. So this is the version currently used by Singapore government, which they use this our engine in the 365 apps for Singapore citizens. So government built this healthy 356 for all the citizens in Singapore to use, and then they provide the incentive for them to use. For example, if they lock the food, right, they will get some small money to buy the food and so on. So all this is done by the government. Then the food engine is basically based on food AI. Yeah. The things I want to tell is basically based on our own build, our own data sets, right? We can achieve accuracy of more than 80 for top 1, more than 95 for top 5, which is very good. But if you look at the images uploaded by the user, right, the accuracy dropped by at least half. Okay, at least half. We only sample a subset of this label and estimate this accuracy. And then from time to time, right, the Singapore Health Promotion Board will tell us, right, our database to have this, why we cannot recognize this, then we improve over time. But just to tell you, for the real world images, right, our result is actually not so good. Yeah, the only thing we can say is top 5 accuracy is like 77%. Yeah, not too bad. Yeah, but in the actual case, it can be worse than this one. So just give you some sense about like why it's so bad. You can look at the second row. Can you differentiate which one is coffee, which one is tea? Yeah, Singapore version of tea and coffee, they're quite similar. Yeah, so that's hard to differentiate. Then the third row is the one I show you, like local people, they order the rice with some dish on top of the rice. Okay, the images here is like lighting condition, so on and so on. So it's hard for us to recognize. Yeah, and then some user also upload incomplete food in the sense that they forget to take the picture before they start eating the food. Yeah, and so on. Yeah. And maybe some user want to challenge our system, so they upload some non-food, or they think that our system can recognize the barcode and so on. Yeah. Some of the food in the last row, right? Anybody know what are the food? Yeah. Until now, nobody in our team can figure out what those food are. Yeah. Anyway, so those are different possible challenges that we have. Okay. So I think it's about time, so I will stop here. Yeah. So see any question you have. So for me, right, the challenge about food recognition is basically robustness, scalability, portion size estimation. Is the things that we need to deal with, but it's so hard. And then where different kind of practical challenge we face, including how to ask people to log the food, is also a big challenge. Opportunity because we have the LLM. As I said just now, it's time for us to connect food recognition and healthcare. So hopefully in the future, we can do something about predictive, preventive healthcare, food recognition, and so on. Okay, I will stop here and see any question from you. Yeah, thank you for your attention. Thanks.
Any questions from the audience?
Yeah.
Thank you for the very interesting talk. I completely agree with you. So we have a lot of work to do.
Yeah.
Well, just curiosity, first of all, what is the interest of the government in order to make people use the app? Just curious. And the other question here is, I like this approach that you are trying to not only to solve critical computer vision problems, but also to make them useful for the society. But my question here is, do we collaborate with nutritionists? That is, how do we know what we are doing, if it is really useful? And sometimes what happens that engineers, sometimes we like obsessed very much in some details, right? Maybe they are not the most important. And there are other details for the nutritionists and dietitians that could be more important in practice. So my question here is how far we are to have something really useful for the society.
Yeah. Let me answer the easy question. What makes Singapore government want to do this, right? Well, Singapore is a small country. Yeah. So we have like 4-5 million population. It's a small country, but the people there, right, is all the while suffering from the chronic disease. Diabetes is one of it. So it's all about food, and it's all about actually local food in the way they cook. Too much sugar or too much salt. So government really care about this. Yeah. So the Health Promotion Board is like they develop their apps. It's not only for food, but also exercise. For example, for me, sometimes I exercise regularly. Yeah, one of the motivation I can get more small money from the government because of the step count. Yeah. So the reason, I mean, the motivation government want to do this, basically, first, chronic disease is getting worse in Singapore. Second, aging population is an issue because Singapore will go into this so-called super aged society after 3 years. It's almost immediately. So government care a lot about this. So there's an agency set up purposely for this, and then they basically launch different campaigns for this. Yeah. Hope I understand answer your first question. The second question is quite challenging. Yeah, we do have dietitian involved sometimes. So what dietitians say is something quite delicate. They say your system can recognize food. Well, most people can recognize those food as well. We don't really need the app to do this because the app sometimes recognize even like the food that it should be recognized correctly. Just because of writing condition, it gives the wrong result. Yeah, so that's one comment from the dietitian. Yeah. The second comment is what dietitians say. What they cannot do is not food recognition. What they cannot do is portion size estimation, because the user or the patient usually just send them different kind of images. Yeah. So what they do is basically they just look at those images. They have a rough idea about what they consume, as well as they look at the color of those images, because according to them, if the images altogether are colorful, could means healthy diet. Yeah. The only thing they cannot really tell is actually portion size. So they really want to push this like portion size estimation. And then we have been trying to work with them, like maybe as what you're doing, using different food model, construct the volume. Yeah. So this method is just too difficult to scale out. Yeah. So my experience with the dietitian is mostly about like portion size estimation. How do we scale out this? If you want to do recognition, food recognition, of course, is also important, but we must make the system robust. Yeah, that's the key. That's why whenever I talk to my student, I emphasize a lot on robustness, scalability, and robustness. Yeah. Hope also answer your question. Yeah. Yeah. Yes.
Yeah, very interesting talk. I think we're sort of seeing the thing now. Yeah, so I'm curious with this app that you're using, do you get any feedback from the people who use them?
Okay, let me clarify. We are not developing apps. We are developing the API service.
I see.
Yeah, for different.
But there is an app. I mean, I see it's something people using on
that's the app developed. That's the app developed by the government themselves.
Okay.
Yeah.
But
so they're basically calling our API.
To analyze the images.
Yeah. So what we do is basically sorry. So let me. Oh yeah. This app is by the government, not by us. It includes not only food. Food is only one part of it. So what they do is basically they call our server. They send the image to our server, and the image will be stored in our server. That's why we have a lot of images. And then we provide 5 results for them. Yeah. Then the user just pick one.
Oh, okay. So there is a feedback from
Yeah, we sometimes will get the feedback like I mean the officer in the agency, they will say, how come your system cannot recognize such common food? Yeah, something like this. So we were something like maybe we need to add in another class to the engine and so on. Yeah.
But what about you also, show, over time you see a very like typical long-tailed distribution, right?
Yeah.
So
Yeah.
like how do you deal with these new foods that or maybe they're not new, they're just a different appearance or different way of people are cooking them, right? But how do you integrate that into your models?
We don't have good solution. As a system, we don't really do anything on long tail. Just on research paper, we try to study this long tail domain adaptation. Yeah, because some of the food is at the tail because they belong, for example, Malay food, Indian food. Yeah, then maybe we can transfer like Chinese food to those food, for example. So that's, I would say that's on research. We don't know how to put everything together a system at this moment. Yeah.
So so is anybody looking at the portion even from like a dietitian point of view? Or it's just, there, the data's there, and then maybe it'll be worked on.
Yeah. So it's quite challenging. For example, when we work with NUS Medical School, right? They usually ask the user to put down something. For example, 1 cup, 1 bowl. Yeah. So 1 cup, 1 bowl is actually is a good tips for us to estimate the portion size. Yeah. For example, just now I showed you the large language model, right? We're trying to use this information to estimate the calorie and
Yeah,
the
it's,
nutrient.
I mean,
Yeah.
sometimes I think it's pretty good results.
Yeah. Exactly. Yeah.
I have two sort of closely related questions. In the earlier talks today, we discussed the importance of food ontologies and food recognition. So do you see any overlap or application of food ontologies to the large language model approach? And second, more practical question, in your evaluation, for example, when you evaluated on Food 101, did you have to do something to enforce that the large language model respects the ontology of Food 101 when it's doing its prediction?
For the first question about ontology, right? We haven't really worked on this. To tell the truth, is actually we come up with different so-called ontology. Those are just like how do we categorize local food in Singapore, Malaysia into we hope we can do something better since many years ago, but until now it's not very successful. Not very successful means he didn't bring us any significant improvement. Yeah. So unfortunately, we're not able to do anything on the ontology at this moment. Your second question about like food classification 101, that we don't do anything special. When we train the networks, right, we treat it as a VQA task. Basically, use the simplest, the regressive machine. What's the next words or those? Yeah, to do this. Yeah, something very simple.
But given that we have trained on so many diverse data sets, did you not face the challenge that the classes that the model was predicting were outside the Food 101 data?
That's a good question. Yeah, that part I need to ask the student how we do. So we basically just fit everything and then multitask learning. When it become like optimal, yeah, then we got the result. Yeah. Certainly, we still need to do more analysis. At this moment, we know that the conversation is not clean. That's we care about. Yeah.
Thanks for the great talk.
Thank you.
Thank you
very much.
Thank you.
Yeah, thanks. How do I connect here?
Did you join Zoom?
Yes, it's so stopping the sharing is on your side. Or okay, I just okay, thanks.
Right. So welcome everyone. My name is Chris Chernetsky, and I am I'm a master's student at the Vision and Image Processing Lab at the University of Waterloo. And today I'll be presenting our paper, How Much You Ate, Food Portion Estimation on Spoons. The paper has been written predominantly by Aryam, myself, Yuhao Chen, Pengcheng Shi, Linlin Shu, and Alexander Wang. So traditional ways of portion estimation rely on tracking. Sorry, something's wrong. We have like two dominant traditional ways of portion estimation, either pre-meal, post-meal photo captures or usages of wearable tracking devices, or just tracking stuff from the nutritional content labels. It can be done if you're a healthy person and if you have a lot of time, if you like spreadsheets. But the question is, what about children? What about the elderly who are aging at home? So when it comes to human eyes, we lack the ability to accurately estimate volume or the nutritional content using our vision. Well, the traditional nutritional content tracking is often inaccurate. Not always the entire portion of the meal is consumed, and sometimes food items can be submerged in a stew or in a soup. The question is, can computer vision-based solution do a better job of nutritional content estimation tracking than a human being could? Our goal was to develop a vision-based nutritional content tracking system that elderly people could use comfortably at home. We have envisioned two principles, essentially make it as seamless to use as possible. So set it and forget it. Imagine a camera that is placed in one location and you don't need to move it. Also minimal interaction. So the best interface for an elderly person is essentially no interface. So one of the biggest challenges that our work is addressing are things like that. So what do you think this is? Like, what do you think this dish is? Any ideas?
Chili?
Well, close enough. It's basically baked beans with some tomato sauce. So if you go back to this photo and if you look at this, it's not very clear from the photo that we have to do with beans in the first place, right? The moment we put it on the spoon, it becomes apparent that we do have actual beans in there. So the thing with elderly people who are aging at home, they will be predominantly consuming things that are more fluid. So soups and stews are going to be a very popular choice for them. And whenever we use photo-based tracking, we risk the inaccuracies because, well, we cannot see everything that is submerged. So what we propose is essentially tracking the nutritional, tracking the portion on the spoons, on the utensils. And we fulfill our user-friendliness requirements by basically proposing essentially a static camera that is going to remain in one position, and we would monitor the food on the spoon or utensil. As a first step, we tried to split video captures taken from YouTube of people eating into frames, and we would independently process them using grounding dyno and segment anything in high quality. Our final prediction mean absolute percentage error ranged, unfortunately, between 160% and 831%. And the prompt that we used for the segmentation model was plainly face, spoon, and food. Here we see an example of a person who has been misclassified as a food item. Then we sort of came back to the drawing board and we asked ourselves the three more important questions. First, when do we start tracking? Second, how do we handle inconsistent predictions frame to frame? And how do we approximate the volume on the actual utensil? We came up with the following pipeline. I don't know if you can see my mouse here. We start with a video capture, which we either process independently frame by frame using Dyno and HPSM, or using video object segmentation using XMEM. Then we feed these inputs to the keyframe detection algorithm, which I'm going to explain in a minute. We perform the extraction of the utensil mask. And finally, we fit parametric shapes on top of the utensil food pair. Our keyframe detection algorithm essentially figures out at what point we should start tracking. We first calculate the distances between the centroids of the utensil and food instance. So for example, if we have in this picture two different spoons, we would like this spoon to be detected as the spoon that is actually traveling to the mouth, right? So what we can do is essentially take centroids of each of the masks, so the utensil mask and the food mask, and calculate the distances. So for this pair of utensil food instance, the segmented instance, we get the shortest distance. Then we also select the pair of utensil and food instance that is actually closer to the subject's face. That's why we also segment the face of the subject. In this case, for instance, you can see that as the utensil is traveling to the mouth, the distance is going to become shorter and shorter. We use essentially right now a fixed cutoff point where we start tracking this as a utensil that we're going to estimate the volume for. Computing the centroids on that segmentation masks actually results in a huge error. So what we want to do is we want to reject also the unreasonable segmentation masks. But what is reasonable, right? In this case, for instance, you can see three examples. The first one is what I've shown before, which is a correct segmentation. We have a food instance here, a utensil here. Here is the entire person segmented as food, and here the hand is also segmented as food. So we want to essentially reject the two latter ones. And to this end, we have used some heuristics to basically help ourselves. In the case of spoons, we have to do with volumes that are in the range between 0 and 15 milliliters. So we took a little bit of a higher threshold of 25 milliliters. And for 5 consecutive volume estimations, if we encounter 5 unreasonable frames, we will just set the predicted volume to 0. So that's the situation where, for instance, the person is not placing the food on the utensil anymore. In the other case, we just reuse the past predictions. This way, we remove frames such as this one, where obviously, like if we use the volume estimation method here, the volume of the food instance is going to be way, way above 25 milliliters. And here are our results. So we have performed an ablation study to see which of the shape approximation methods and whether the usage of the video object segmentation helps or not. And we have found that ellipsoid approximation performs best. With the filtering algorithm on, it's the best method. It outperforms marginally even the video object segmentation. One interesting thing to maybe also mention here is that if we take the independent frames processing without filtering, so let's say the hemisphere without filter, our per frame mean absolute percentage error is very high. It's around 950%. But the moment we use VOS, the error drops down significantly, and the filtering for some of the methods of approximation of the volume does not differ that much. Here are also results for the MIOU, so mean intersection over union for the split and food classes. Essentially, when processing independent frames, the MIOU is higher, which indicates higher precision. For VOS, it's a little lower. We also present in our paper the results for the best frame. So if we were to pick out from a video capture the best frame estimated, we see that the prism method is actually the best. So it's essentially overfitting to the shape. So to summarize, we have proposed an end-to-end volumetric estimation pipeline for food present on spoon. Our approach is non-invasive and requires minimal interaction from the user to remain effective. Our approach also solves the problem of tracking partially finished portions, hard to estimate meals such as soups and stews with submerged solid parts. As next steps, we would like to explore other aspects of eating. So we would like to extend the method to other utensils, such as chopsticks, for instance. Another concept that we need to also address is the fact that we also often use our hands as utensils. And that's very prevalent in Indian cuisine. But also when we go to a burger joint and we order a burger, we also use our hands. There are also food types that extend way beyond the utensil volume. So for example, spaghetti noodles, how do we handle them? We've got some media attention. Professor Yuhao was talking to New Scientist, and we got an article in New Scientist and also in Sky News. So if you're interested, here are the QR codes for this. All right, moving on. Yeah, so that's about it. If you have any questions, I'm happy to answer them. Thank you. Yes.
So for the best frame volume errors that you reported, you're assuming that the ground truth is exactly the volume spoon.
So, well, the way we estimated the volume of the spoon, well, we use certain heuristics in there, right? So, for example, when you have the camera positioned en face towards the person who is consuming the food, right? We assume that the person is essentially lifting the thing vertically, right? That there are no slants or whatnot in the perspective, right? So we also assume then the length of the spoon is exactly 3.81 centimeters, which corresponds to a typical tablespoon. So there are some heuristics that we would need to address and probably change to be able to support other types of utensils. As for the best frame prediction, is basically for every frame we calculated the metrics and we picked out the best one against the ground truth with the mask that was drawn. Yeah. Any other questions?
Yes. No question. I understand it's quite difficult to estimate in the spoon, and even when you say that this is you need to think about fork, etc. Isn't it easier if you estimate the food before and after? No, I estimate the leftovers, and then from this compute how much food was taken.
Yes, it's one possible way of doing that. It's maybe not necessarily as resilient to the submerged parts in food, right? Assuming, for instance, a person has consumed only a couple of bites and then they refuse to eat more because they don't like the taste of the food, or I don't know, for some reason they just don't feel hungry. In the post capture, it would still be hard to detect, for instance, the solid pieces of chicken in the chicken soup, right? Unless there is enough liquid that has been consumed or dumped. It's all about also the fact that we want to make it as non-invasive as possible, because if elderly individuals aging at home are going to be subjected to certain procedures like these, it feels a little bit invasive. It's already a big intervention to put a camera in somebody's face and track their eating all the time, right? So we want to minimize this sort of discomfort.
Great, thank you.
Thank you.
All right, exciting time. So finally, we will announce the challenge winners, and then they will present their methodologies. So, all right, so share this. Okay, so a brief description. Can online audience see me? See my slides, me slides? Can you see me? Okay, good. So, so we are hosting the MetaFood Workshop. One of the challenge that we host with to promote the MetaFood, the meta part of our workshop, is we want to be able to do food portion estimation using 3D prior knowledges, especially given the recent trend of the computer vision community looking at all the surface reconstruction, mesh reconstruction from neural radiance field and the Gaussian splatting. And then that's the reason that we work with Purdue University and then come up with this challenge, which is a physically informed 3D food reconstruction challenge. The goal of this is that we hope that the team will reconstruct food mesh with while providing very accurate size estimation for the food. And then we even further designed different level of difficulties by providing participants with different amount of input images. So there's some of the images are like some of the food objects we provide about 200, and then for the difficult one we only provide about one of them. So this is a kind of a new problem designed for the community to look at this 3D food portion estimation. So we are very glad that it went very well. And then here we are to announce the winners. So the first prize, the first place goes to Team Vol ETA from University of Barcelona. Congratulations. Thank you. And then the second place award goes to Beijing Institute of Technology from China. Congratulations to the team ININVIAUN.
Thank you, Professor Chen.
Yes, no problem. And then the final, in addition to the main task we do, we also recognize people who spend effort to reconstruct, put effort into reconstructing good object meshes. So we create this Best Mesh Reconstruction Award to acknowledge the efforts for the following food riddle team. They are from Baidu XPeng and Beijing Institute of Post and Telecommunications. Congratulations. So next I will thank all the challenge organization team, especially the students Gotham and then Toha for putting the effort and then running everything. Thank you for the organization team. All right, so now the exciting time has come. Let's hear about the winner solutions. So we will start with the best mesh reconstruction team, which is Food Riddle. Then we go to the second place awards team, Team ININ, and then finally we will go with the University of Barcelona team. Thanks. So I'm going to stop sharing here. And let's yes. So can Food Riddle team present?
Yeah, Can you see it now?
The food radar team will be the first team. Thank you. Is the food radar team here?
Can you hear me? Yeah, I'm here. I'm trying to open the PowerPoint, but there's some problem with.
Yes, maybe let's start with the second place team, the IN team from Beijing Institute of Technology. Jia Dongtang.
Yeah, I'm here. Mm. Mm. Yeah, thank you, Professor Chen. I'm very grateful for the efforts made by the organizers, and I'm honored to receive the invitation to give this presentation. On behalf of the INVION, I will give a brief overview of our workflow for the competition. The technology of accurately reconstructing 3D food models is crucial for tracking nutritional intake and aiding individuals in maintaining a healthy diet. When applying some advanced methods to food reconstruction, we will still encounter some issues. These include difficulties in accurately determining the scale factor of the reconstructed scenes, deviation in the geometry of the reconstructed objects, and the uncertainty of reconstructing unobserved areas. Next, I will introduce our method. We estimate the scale using a corner projection matching method. First, we obtain the image sets with intrinsic and extrinsic parameters and a dense point cloud via CoMap. Then, we detect corners in bandarized images. Using the camera parameters and the pixel coordinates of the corners, we calculate the corresponding spatial coordinates using the perspective projection model. By analyzing the distance between these points, we can estimate the final scale factor. Then I will introduce the pipeline we used in the reconstruction process. For the first 15 objects, we use CoMap to estimate the poses and then reconstruct the segmented food. In practice, we employ 3 different reconstruction methods. After that, we scale the extracted mesh using the estimated scale factor. Finally, we apply some optimization techniques to obtain a refined mesh. And for the last 5 single view objects, we use an advanced single view reconstruction method, 0 MVS. However, due to the limitation of single view, we need to incorporate the depth information from the dataset and the checkboard in the monocular image to determine the size of the mesh. Similarly, we apply some optimization techniques to obtain a refined mesh. For the holes in the mesh caused by invisibility, we perform repairs to obtain a waterproof mesh. Additionally, we smooth the surface of the mesh to make it look more realistic. The estimated scale factors are shown in the table below, and these are the final meshes we submitted. In the process of aligning our models with the ground truth, we first align with the centroids. Then we use SAP registration for further alignment. Finally, we apply gradient descent to obtain the final transformation matrix. In conclusion, we would like to once again thank the committee for their efforts in organizing this competition. And we believe that the dataset will greatly contribute to high-quality food 3D reconstruction. We are honored to have achieved the second place in the competition, and look forward to having academic discussions with other teams in the future. Thanks for your time.
Thank you. Are you guys able to open the camera? We can take a picture with the screen.
Yes.
Amy, can you take a picture of it with the screen?
Can you see me?
All right. Congratulations.
Yeah, thank you.
2, 1, smile. Oh, so cute. Okay, cool.
All right, moving on. Maybe let's go with the first place award winner, which is from the University of Barcelona.
Hey, I'm back. Maybe you want me to the presentation first, or I'm
maybe
from the food radio. I had some connection problem.
Can you present last? That would be
Oh
great.
yeah, I can also do that. Of course.
Next to the first place winner. Thank you. Hello, we can't hear you. Enable your meeting. Can you join again? I can't see. The red button.
Just try pressing the mute. Oh, that's you can't.
Yeah, we can also change the-
Wait, same host.
Something, do you have the email?
Who's the host?
It's the third guy.
Yeah, ask them to go mute them then.
Can you join again? Try to join again. Thank you. Maybe they can resume the video one.
Because if you click on the unmute, for example, for Jesus, can you unmute him for that?
I can, no, not, I don't think anyone. I can mute myself. But I don't want to mute myself. Okay, maybe we start with food riddle. Sorry for the technical difficulties. Yeah, food riddle, can you start? Yes, yes, the presentation was working.
Can you see the PowerPoint?
Thank you.
Yeah, maybe this one here. So, good afternoon, everyone, and good night, maybe to somebody else. My name is Yawei Jueluo, and these are my teammates, Cheng Yushi and Peng Yuwang. We are from the team Food Radio, and it's an honor to be here to present to you with our work. So the challenge, we are addressing device input data into 3 different categories: input, easy, medium, and hard, each defined by the number of input images. But we are using only 2 pipelines: the multi-view reconstruction for simple and medium, and single view reconstruction for the hard. And the primary difference here is that we use different primary informations to complete the occluded part. So here, the multi-view reconstruction consists of 3 different stages. Firstly, structure from motion, then the mesh reconstruction to get a raw mesh, which is not complete, and as you can see in the figure 5. And then we will use some extra information with prior to complete the mesh. So in the structure from motion stage, we will get the camera poses and some feature points. And the challenge here is that there are some low texture areas. So we are using CodeMap as framework, but the vanilla CodeMap can't handle this kind of areas very well. So we change the feature point and the descriptors to a learning-based method, especially the super point and super glue. As you can see in figure 7, this change will significantly improve the results. And for the mesh reconstruction, there are more challenges, such as reflections, complicated local structures, distortions at the boundary with some with the supporting surface, and some occlusions. And we employed the 2D Gaussian splitting method, and because which actually provided some regularization terms for the depth distortion and normal consistency. And this could reduce the noise, but it's still not enough. So we had the 3rd stage, which we will furtherly refine mesh. So the first step is to apply some filter and outlier removal techniques to furtherly denoise the mesh. Then we will calculate the contour of the supporting part. It's like firstly fitting the supporting surface, which could be the plate or the table. Then we will apply the non-maximum suppression to the lower point of the mesh, projected on the surface. And then we will use their local geometry, structure, and their distance to the surface to estimate the supporting contour on the plan. So is as you can see in the figure 8 from the left, firstly, the input is an incomplete mesh. Then we will project them onto the plane, just like shown in the figure 9. And the green part, the green points are the control points we get after this process, and which is the central part of the figure 8, the points under the gray strawberry. And finally, we will use a Poisson reconstruction to guide to get a complete and watertight mesh for the whole subject. And for the single view reconstruction is something very similar, but the difference is that we are using some content generation methods to get the mesh, which are instant mesh and LGM. We will generate a series of candidates and go through a candidate selection procedure to find the best one. And then we'll apply some similar method, similar post-process and scaling method, just like for the multi-view construction pipeline. So with the method mentioned above, we have achieved the lowest error in both multi and single view reconstruction. So here are some videos to show our results. And we are honored to have this received this award, and sincerely thank the MetaFood committee for your recognition, and also from our competitors. And thank you for your listening.
Thank you. Can you turn on your camera? Then we take a picture. Thank you. Oh, you have to close the presentation, I think.
Oh yeah. Can you see me now?
Yeah.
Oh, that's cute. Bird well.
Thank you. Congratulations. And finally, we have our winner. So can we?
Yeah, here there is a message that the host should unmute. He is not allowed to unmute, but otherwise I can put my phone on.
Okay. Okay. Yeah.
Hello? Hello? Hello?
Can you hear me?
Yes.
Perfect, finally.
A little bit technically.
But
somehow I cannot unmute myself.
Can you
share?
you should share the screen?
Yeah, I will share my screen. Okay, can you see my screen?
Yes.
Okay, perfect. So yeah. So good morning, good evening, good afternoon, everyone. Wherever you are in this vast world, my name is Ahmed Al-Mourabi. I'm a PhD candidate at University of Barcelona. Today, I will explain you our one and few shot approach for food volume estimation. Because the number of images are large, our approach started with key frame selection to minimize the number of images with the highest possible information. We simply remove the blurry images using defocus blur, and then we remove the highly overlapped images using near image similarity. Next, here we go. We run in parallel our two-step phase. The first step is pixel SFM for camera pose estimation, and the second step is for reference object segmentation. Where we segment the first mask using the segment anything with the segmentation prompt, and track it using Xmin2. So we have a set of masks for the reference object. Once the two-step phase is finished, we model the data for News2. News2 will generate two meshes, a mesh for reference object and a mesh for food object. Next, we clean up the isolated pieces of size less than 5% for each mesh. Furthermore, we manually identify the scaling factor using MeshLab for the reference object mesh, and fine-tune the scaling factor using the depth information, and apply the scaling factor on the food mesh. Finally, we extract the scale mesh volume. Okay, for one shot food volume estimation, We use 1, 2, 3, 45 model to generate a 3D mesh for a segment image, and then we clean up the mesh. After that, we identify the scaling factor from the few shot food volume estimation and finely tune them using the depth information. We then apply the scaling factor on the food mesh and extract the volume. Here, we show phase 1 results. We show our scaling factors per pixel unit and reference dimension and food dimensions and volume results for each object. Please note that the scene 12 and 15 are excluded from the challenge. Next, here we show our phase 2 results, ground truth, our volume, the chamfer distance results with and without transformation metrics. We use ICT to register our meshes and the ground truth, our meshes and the ground truth for obtaining the transformation metrics. We show the both average and sum metrics for all scenes. Here we show our reconstruction comparing the ground truth. Notably, our meshes has 512 by 512 resolution. And here we show our constructed meshes from different angles. We can see that our approach can fairly reconstruct unseen parts of the food. And finally, meet our team. If you have any question, I know I moved very quick for the approach. If you have any question, please don't hesitate to reach us. Thanks for joining.
Thank you. Congratulations. Can you turn on your camera and then can you turn on your camera? Show your face.
You cannot open my mic, and neither I cannot unmute or cannot open the camera. So I can show, maybe I can show myself in my phone here.
This page.
It will not be okay.
Oh,
Oh.
okay. We
Okay,
just
okay.
have a picture with this slides.
Amazing. Yeah, perfect. Wow. Perfect.
Thank you. Thank you.
Congratulations. Congratulations to all the teams. And that concludes our MetaFood workshop. Thank you all for coming, and then we hope we will see you next year.
Another way to.
Oh, by the way, we here's an ad for the sensors open access journal, and then there's a call for paper for smart sensing for dietary monitoring. If you are interested, I have some flyers. Please consider submission.
I expect to see you here.
Yeah.
I'm actually working in Seattle.
I'm gonna try and see if I can.
Yeah, for my follow-up. No, I just paid because I think it's.
We're gonna disperse it. Let's go down to the first.
Can I get one too?
You want it to be sweetie, please? That would be more. Yeah. Okay, sorry.
You are still sharing your screen?
Congrats on hosting the workshop. Is this your first workshop?
What?
Yeah, this is
Okay, I'm
my first time coming to a conference. So.
Oh, CVPR, yes.
Yeah.